Hello viewers, we are here again to show you how to solve linear programming problems using Simplex method.
Linear Programming Simplex Method. It is an approach to solving linear programming models by using slack variables, tableaus, and pivot variables as a means to finding the optimal solution of an optimization problem. A linear program is a method of achieving the best outcome given a maximum or minimum equation with linear constraints. To solve a linear programming model using the simplex method, the following steps are necessary. Standard form, introducing slack variables, creating the tableau, pivot variables, creating a new tableau, checking for optimality, and identify optimal values.
So in this tutorial, we are going to solve the previous problem we had using the Simplex method. So the first step of the Simplex method requires that we convert each inequality constraint in an LP formulation into an equation, and in our problem we are already given the objective function, so we can directly convert the constraints into equations. So less than or equal to constraints, such as in the personal mini warehouses problem, are converted to equations by adding a slack variable to each constraint. And as you can see, we added a slack variable to each of the constraints. So S1 for the first constraint, S2 for the second constraint, and S3 for the third constraint. And because slack variables yield no profit, they are added to the original objective function with zero profit coefficients. So these slack variables represent unused resources. So this may be in the form of time on a machine, labor hours, money, warehouse space, or any number of such resources in various business problems. So in our case at hand, we can let S1, the slack variable representing unused advertising budget, S2, the slack variable representing the unused square footage required, and S3, the slack variable representing unused rental limit. To simplify the equations and objective function in an LP problem, we place all of the coefficients into tabular form. So the first simplex tableau is shown in this picture. So we can complete the initial simplex tableau by these last two rows that provide us with important economic information, including the total monthly earnings and the answer as to whether the current solution is optimal. So we can solve the ZJ by using the formula shown in the picture. ZJ equals monthly earnings per unit of S1 times substitution rate in row 1 plus monthly earnings per unit of S2 times substitution rate in row 2 plus monthly earnings per unit of S3 times substitution rate in row 3. So for example, in the ZJ for column X1, 0 times 20 plus 0 times 100 plus 0 times 1 equals 0, and the ZJ for column X2 equals 0 times 40 plus 0 times 50 plus 0 times 0 equals 0. And just continue the same process until the column for quantity. The CJ minus ZJ number in each column represents the net profit, that is the profit gained minus the profit given up that will result from introducing 1 unit of each product or variable into the solution. So to compute these numbers, simply subtract the ZJ total for each column from the CJ value at the very top of that variable's column. So in this example, we have here 50 minus 0 equal to 50, 20 minus 0 equals to 20, 0 minus 0, 0, and so on. After completing the whole table, we will now identify the PC or the pivot column by identifying the column or the variable with the largest positive number in the CJ minus ZJ row of the preceding tableau. So in this problem, our pivot column is in the X1 column since 50 has the largest number or is the largest variable in the CJ minus ZJ row. So the next step is to Know your PR or your pivot row by dividing each amount in the quantity column by the corresponding number in the pivot column. So the row with the smallest non-negative number calculated in this fashion will be replaced in the next tableau. So in this problem, we have here 4,000 divided by 20, we have 200, 8,000 divided by 100 equals to 80, and 60 divided by 1 equals 60. So the smallest non-negative number is 60. So that row will be your PR. So to identify our PN or our pivot number, we have to see or to look at the number which lies at the intersection of our PC and PR. So in this problem, our PN or in this tableau, our PN is 1. So in the second tableau, we first have to decide which of the variables will enter the solution next. So we have to select the one with the largest positive Cj minus Dj value. And since in the first tableau, the largest positive Cj minus Dj value is 50. So we choose x1 to enter the solution mix with a Cj of 50. And we have now to compute the new values for the pivot row. So to do this, we simply divide every number in the row by the pivot number. So in this tableau, we can see that our PN in the first tableau is 1. So we just have to divide each number in that row by the PN. So 1 divided by 1 equals 1, 0 divided by 1, 0, 0 divided by 1, 1, and so on. And so to compute the new values for each remaining row, we just have to use the formula in getting the new row number, which is equal to number in old row minus the number above or below PN times the corresponding number in new row. So in solving the new row number of S2, we have here the number in old row, which is 100 minus the number above or below PN, 100 also times corresponding number in new row, which is 1. So 100 minus 100 times 1 is equal to 0. So it is 0 in the column for x1. So the next column, the number in old row, which is 50, minus number above or below PN, which is 100, times the corresponding number in new row, which is 0. So it is 50. So you just have to do the same process in the remaining number in that row and as well as in your row S1. And after that, you also have to get the Zj, since we already know how to get the Zj, and also the Cj minus Dj value. And for this second tableau, we have already identified our pivot column, and after that, we divided each of the quantity in the right hand side by the numbers in your pivot column, like 2,800 divided by 40, which is 70, 2,000 divided by 50, which is equal to 40, and then 60 divided by 0, which is undefined. And from this, we have identified our pivot row and our pivot number. So from this tableau, we still have to go to the third tableau since all the numbers in our Cj minus Dj row are not yet negative or 0. So for the third tableau, we have a new variable that entered the solution mix. So it is x2 with a Cj of 20. And for the remaining values for that pivot row, we simply divide every number in the row by the pivot number. So for example, we have here 0 divided by 50, which is 0, 50 divided by 50, which is 1, 0 divided by 50, which is 0, and so on. And then we compute for the new row number for the remaining row S1 and row X1, and after that, we also compute for the Zj and Cj minus Dj. And since all the numbers in our Cj minus Dj row are 0 and negative, we now have reached the optimal solution of the problem. And from this, we have a z value for $3,800 with an x1 which is equal to 60 and x2 which is equal to 40. And to verify the answer, we substitute the x1 and x2 to our objective function, and then we get $3,800.
The second problem is about minimum cost in a business application. So first, I will read the problem. A small petroleum company owns 2 refineries. Refinery 1 costs $20,000 per day to operate, and it can produce 400 barrels of high-grade oil, 300 barrels of medium-grade oil, and 200 barrels of low-grade oil each day. Refinery 2 is newer and more modern. It costs $25,000 per day to operate, and it can produce 300 barrels of high-grade oil, 400 barrels of medium-grade oil, and 500 barrels of low-grade oil each day. The company has orders totaling 25,000 barrels of high-grade oil, 27,000 barrels of medium-grade oil, and 30,000 barrels of low-grade oil. So how many days should it run each refinery to minimize its cost and still refine enough oil to meet its orders? First, in solving this problem, we should determine its objective function and its constraints. So we let x1 and x2 as the number of days of the 2 refineries that should be operated. So the objective function is minimize z is equals to 20,000 x1 plus 25,000 x2, and it is subject to the 3 constraints, which is for the high-grade oil, medium-grade oil, and low-grade oil. So for high-grade oil, we have 400 x1 plus 300 x2 greater than or equal to 25,000, and for medium grade, we have 300 x1 plus 400 x2 greater than or equal to 27,000, and for low-grade oil, we have 200 x1 plus 500 x2 greater than or equal to 30,000. And x1 and x2, it must be greater than or equal to 0. After determining its objective function and its constraints, we now proceed in making its augmented matrix. So this is the augmented matrix. So after making this one, we should know the matrix corresponding to this dual maximization problem. So the steps in finding this is just the same with the previous problem. Now we apply the simplex method to this dual problem. So first is we choose the variable with the greatest negative. So the greatest negative here is negative 30,000. So we highlight this column. So after that, we select the row with the smallest non-negative ratio. So in computing or in determining the smallest non-negative ratio, we just divide the quantity column by the corresponding number in the column selected in step 1. So in this problem, the smallest non-negative ratio here is 25,000, and we should highlight this one. And after that, the common value here is the number 500. So 500 there is our Pn, in which Pn means pivot number. So after determining its pivot number, we now compute new values for the pivot row. So to do this, we just simply divide every number in the row by the pivot column. And after that, we compute also the new values for each remaining row. So in computing those new values, just like this previous problem or the steps in the previous problem. So after obtaining the new values, so now we have these values. For x1 we have 280, 3 over 5, and negative 7,000. For x2 column, we have 140, 4 over 5, negative 3,000. For x3 column, we have 0, 1, 0. For s1, we have 1, 0, 0. For s2, we have negative 2 over 5, 1 over 560. And for quantity column, we have 10,000, 50, and 1,500,000. So still the same, we have still the same process. We obtain the pivot number of 280. So after that, we compute again, or the same process we do in the first tableau. So in the next tableau, we should obtain again new values. So in the third tableau, we could see that we have a positive value and zero value. So in a minimization problem, it says that an optimal solution is reached already when all the numbers in that row or in that last row are zero or positive. So we now reach its optimal solution, in which x1 is 25 and x2 is 50, and the z value here is 1. Now we obtain the minimum z value, or minimum cost value, is equals to $1,750,000, and x1 is equals to 25 and x2 is equals to 50. So x1 is for refinery 1 and x2 is for refinery 2, meaning these numbers are the days that should the two refineries be operated, and also that we could obtain also or produce the following amounts of oil if these two refineries will operate this number of days. So for high grade oil, we could produce a 25,000 barrels. For medium grade oil is 27,500 barrels, and for low grade oil, we can produce 30,000 barrels. So in solving this, we just substitute the x values to the constraints of, or the equation of the constraints.
Thank you for watching our video.
You can leave some questions and clarifications under the comment section below.
Please like and share this video.
And don't forget to subscribe.
Bye, viewers!